Thank you, Chairman. I'm very different from the previous two talks. I'm going to talk about the basic investigation of joint properties for superconducting DC cable application. So, in our group is have been working on the development of HDS DC power transmission system, and this year I show our relatively recent works concerning the power transmission experiment. So these are 500-meter system and a 1 kilometer system. And with this system, we have been performed the cooling test for 3 times for 500-meter system and 1 kilometer for 2 times. So most of them we made in the fiscal year of 2013 to 2016. But this year we had done the cooling test for 500 meters after 5 years of blank. And with this test, we confirmed that there is no degradation of the superconducting properties. This is actually this year's test was line 1, and we confirmed that after 5 years, and also that during these 5 years we had very big earthquake in Hokkaido area, and we saw that the system persists even after this very big earthquakes. Anyway, that we had made many verification tests, and especially we colored with this yellow. So these are about the cooling system, and the important things with cooling system is how we can go to the very long system. So with this number, we can estimate that the feasibility of a 20-kilometer superconducting DC transmission system. And just by very simple calculation, that we think that now we are able to cool down this very long cables with 20 kilometers with existing refrigerators and also existing liquid nitrogen pump. However, the problem is that in spite of the recent rapid progress in the manufacturing technique of high temperature superconducting tape, the tape length is still limited to several hundred meters. So the problem is that we have to join every short piece tapes to make a very long cable. And this is an example for the specification of the cable core which we use for this DC system. So you can see that for line 1 with 5 kiloampere capacity, we need 337 tapes to make up one cable. And line 2 is 24. And we have, this is and totally that we need this number of tapes. So it is a very, very, very big numbers if we if we want to make a very long leg tapes. And here we show the structure of the joint. So actually the joint is made at the side. So cable from came from a left-hand side and right-hand side, and they are joined one by one with the soldering techniques as shown in these photos. So this is very tough, and the problem is that we don't know whether it is very homogeneously made. The joint resistivity is homogeneous or not. So, and anyway, that's at present time, the solder joint technique is widely used for joining high temperature superconducting tapes for the practical use. And From the basic, there is many basic studies about the joint properties, and the problem is the reported value of joint resistivities are widespread, and actually that's a few nano-ohm to 100 ohms. And also that's almost no information about the current density distribution in joint. And here we show an example for our calculation of how the joint resistivities variations affect on the current distribution in a parallel tape. So left-hand side is that we make one joint, two joints, and three joints, and with same resistivities of about 30 nano ohm. And with this variation, very small variation, you can see that the current differs largely by tapes and tape. And this variety gives at the low current, it causes hysteresis loss if we apply a AC current. Okay. So anyway, that because there is no way to make a destructive measurement for these joint properties, we have to develop the way to evaluate the joint properties. So we use the Hall sensor to make the measurement of the magnetic field distribution. Then we convert the magnetic field distribution to the current distribution by solving the inverse problems from the Biot-Savart law. And this is a very widely used way. And as a first approach, we may perform the magnetic field distribution measurement by scanning a three-dimensional whole probe joint area of commercial GDBCO tapes. And by use of this three-dimensional Hall sensor, we obtain three component of magnetization field, Bx, By, and Bz. And thus obtained two-dimensional maps of the magnetic field are used in MATLAB code to solve the inverse problem and obtain current distribution in joint area. And this is an example schematic view of our measurement system. So the HTS tape is immersed in the liquid nitrogen to get superconductivities, and a large current was passed. So we passed up to 150 amperes. Then this is a Hall sensor, and Hall sensor was put on the bar, and we scanned along the Y direction and Z direction. And this is a sample which we use to evaluate the joint properties. So this is gadolinium BCO tapes, which is fabricated by Superox, and also that the joint was fabricated by this team by standard method. And the here we show that transport measured resistivities of these tapes. So the value was 74.2 nano ohm. I think this is a relatively standard value. And here I show the analysis of current density profiles. So for detail, please look at these references as shown here. So this is a measurement result, and left-hand side is the transport current dependence of Bx. So Bx is Bx is the magnetic field direction along the length direction. And you can see that at the edge of both joints, there is some big kinks in the magnetic field. And especially at the 100 amperes, it shows a very big changes in the magnetic field directions. And also for the right hand side, the magnetic field was depressed at the place where we have the joint. It is very remarkable in the case of 100 amperes. So this is very strange from our expectation. So from right hand field, right hand figure, that it seems that the current magnetic field is the upper tapes repels the magnetic field from the lower tapes. So then we using this data, we made the calculation for the current densities. And the left hand side is 75 amperes and the right hand side is 100 amperes. And we only see the, we made this, the current profiles, which is going vertical for the joint. So it means that the current transfers from lower tapes to upper tape. And what is interesting is that we only see the big current transferring at the edge of the joint, and especially at the downstream side of the joint. So this is very different from our expectations at the joint. We thought we expect the current from transfers very uniformly from the lower tapes to the upper tape. But in fact, this results show that the current transfers only at the edge of the joint. So using as a summary, using 2D mapping of three components of magnetic field data, we successfully obtained transport current profiles at the joint area of gadolinium VCO tapes by solving the inverse problem. The current is likely to transit from the first tape to the second tape at the joint edge and at the downstream side. The measured sample gadolinium VCO. So anyway, this is only a very simple measurement, and I think that to make a conclusion, we have to measure much more in the using the different sample. But anyway, what we can say is that current flow at the joint is not so simple, and we have to take more care to the joint properties. That's all. Thank you for your attention.
I wonder at the last slide before summary. Yeah, so these two graphs, left hand side is not pressed. The right hand side is pressed, right? Between two slab joint.
Sorry, please say again.
Yeah. Or what's the difference between two graphs?
Yeah.
Left side
Mm.
graph, right side graph.
Difference is current.
Only current, right?
Yes, only current. Yes.
What about the y-axis? Y-axis is the slab width.
Y-axis.
Y-axis, like
Y-axis current density. You mean?
no, y is in millimeter.
Sorry. And yeah. Yes. Sorry, I didn't show. Yeah.
I think it's thickness direction. Oh, width
Yeah.
direction.
Sorry, I didn't show. So you want the edge position. So it. Sorry, I didn't show.
I ask because x is equal if x is equal to 28 millimeter, the current density is highest. So is it
Yes.
optimum joint length? Because if it is 26 millimeter, it's lower.
Yeah.
32
So
is lower.
sorry. So I need to show this one. So here, this dotted area is the place where we have the tapes, and the tapes y-axis is from 8 to 12.
Yes.
And
in width direction.
and x direction is 0 to 30.
So optimum joint length is 28 millimeter, right? From this graph.
This is not the joint length. The current at the, so this means that x, so we made a measurement for each slice. So x equal to 10 or 12. So this is
I see.
current profile for the x20 or x30 or like that. So current flowing, this is current profile.
Yes.
This is calculation.
So this x28 and 30 is not the length.
Calculated
Joint length.
transfer.
Sorry?
Not measurement. This is calculation, I think, not measurement.
But this this is a calculation. But
Yes.
this was we calculated from this data. So
Okay.
magnetic field distribution data.
Thank you.